First, are there any questions or concerns? Can you hear and see me? Is that a yes or no? Wendy, can you hear me?
Now I can.
Okay. You're the only face I can see. Okay. So the goal today is to finish chapter 2 and start chapter 3. So we had just summarized the different reactions. So we have exergonic reactions and endergonic reactions. What's the difference between those two? Someone tell me, what's the difference between those two?
Release of energy versus input of energy.
Yes. So exergonic, good job, Raiden. Exergonic is a release of energy. Endergonic is energy being required or being absorbed into the reaction. So an oxidation reaction, which is to remove electrons, is an exergonic reaction. A decomposition or a catabolic reaction are to break things down. Synthesis or anabolic reactions are to build things up. Things that influence reaction rates or factors that influence reaction rates are temperature, because temperature can introduce kinetic energy. If you think heat, noodles boil a lot faster when there's heat. They might get cooked at some point, might absorb all the water at some point. If there's no heat, but it's not going to happen very fast. Concentration, the more reactants or the more particles there are, the more likely they are to react. Size, the smaller the size, the faster things tend to move, and the more stronger they tend to collide. And catalysts, enzymes, so substances that will increase the reaction rates but won't be chemically changed by the reaction. They also, with regards to enzymes, we have cofactors and coenzymes that are required by enzymes to allow them to do their functions. First and foremost, differences between inorganic and organic compounds. Inorganic compounds are simple structures that are small in size with few atoms involved. And they tend to be bound by ionic or covalent bonds. Some examples are water, sodium chloride, and carbon dioxide. Organic compounds are carbon-based, and they must contain hydrogen. So if you are asked on a quiz or an exam, if a given compound is an organic molecule, if it does not contain both carbon and hydrogen, it's not an organic molecule. It has to contain both carbon and hydrogen. So organic compounds contain carbon and hydrogen. They're chains of carbon atoms. And they also contain nitrogen, sulfur, phosphate, and oxygen. They can contain that. They're usually large in size. They're complex structures. And they're always bound by covalent bonds. So inorganic can be ionic or covalent bonds. Organic compounds are always covalent bonds. Some examples are macromolecules and polymers. So why organic chemistry is the basis of life? And why is it carbon? Why isn't potassium or zinc or chloride? What's unique about carbon that allows this to be the basis for all organic compounds? Carbon, if you remember where that is on the periodic table, it is over in the upper right corner where our really electronegative atoms are. However, it's not electronegative. It's what we call electroneutral. It never loses its electrons. It only shares them. So it's never capable of making an ionic bond. The bonds that it makes are never polar. They're always nonpolar.
And is that because, like, each carbon atom, for instance, they can form 4 different chemical bonds as far as sharing them to other atoms then?
Well, they can only form covalent bonds. And the major reason it's considered a neutral atom is because it doesn't lose its electrons and it can only share them. So it has no ability to ionize. One of the possibilities for why someone in one of my classes mentioned this, and I thought, well, maybe it's a possibility. So one of the ideas as to why it always shares them and never loses them is carbon has 4 valence electrons. It binds with 4 other atoms so that it can receive 4 more electrons to fill its valence shell.
That's what I was trying to say. Okay. Thank you.
You're welcome. Now, this is my question for you. So if you remember Jade, this is my question for you. So atoms that have 6 valence electrons tend to easily gain 2. Atoms that have 5 valence electrons easily gain 3. Atoms that have 1, 2, or 3 electrons in their valence shell tend to lose them. Is that why carbon always shares them, is because it has 4? Because it's right, it's not thermodynamically stable for it to lose the 4, and it's not more thermodynamically stable for it to gain 4.
So then I'm going to say no to that because they share off.
Well, I personally, this is what I think, is that, because it's not easy to lose 3, for certain atoms that have valence electrons that have 3, it's easier for them to lose those 3. If they have 5, it's easier to gain them.
Gain them. Okay.
But now we've got an atom that has 4.
Okay.
And whether or not that's the case, I don't know. Because I can't remember what's below it on the periodic table. But it also has 4 valence electrons. Everything in that group has 4 valence electrons.
Okay.
Whether they all do that, I don't know. But nevertheless, it never loses its electrons, it only shares them. It's electroneutral, so it doesn't ever form polar bonds. It's also very versatile because it can form 4 different bonds. So what elements must an organic compound contain? Go up and look, like on the 3rd slide up.
Is that hydrogen, oxygen, or nitrogen?
Nope, it's just hydrogen and carbon.
Carbon, yeah.
Just hydrogen and carbon. What types of bonds does carbon form with other atoms? Becky, what types of bonds does carbon form with other atoms?
Is it the covalent?
It's a covalent, right? How many bonds is it capable of making?
Covalent bonds. How many bonds?
If it has 4 valence electrons, how many more does it want? So
4.
Yep,
So once it can make up to 4.
yep, it can make up to 4 bonds. What types of structures can be made with carbon? Well, lots of different structures. We can form chains with carbon, hydrogen. We can make double bonds between carbons. We can do branching or unbranched. We can do rings. Now, of all of these structures right here, what ones are polar?
What was the question? You said which ones are polar?
Uh-huh. That's the question. What do you have to be a polar molecule?
Finding the difference between the
You're on the right, the electronegativity.
of the atoms.
Right. So looking here, what ones are polar? Abby, Mom, if you don't want her in your room, go close your door a little better. Sorry. My mom's room is a cat-free room, and I'm watching my cat go in there because it's the one room she can't go in, so it's her favorite room.
That's a question before I answer that.
Go.
Isn't it if like the result is something between like 0 point, if I'm not mistaken, like 4 and 1.7, then it's generally the bond is polar, correct?
Yes, but let me tell you that what I asked you was a trick question.
Okay, that's what I figured. That's why I was like, can I ask a question before I answer that?
Because carbon is neutral, and so is hydrogen. Now, unless you have something that's polar, it doesn't have, if it's not polar, it doesn't have a charge, no partial charges, no no hydrogen bonding is going to occur. So what kind of reactions do you think we get with these molecules alone? The only ones we're really going to get are with these molecules and other molecules. So this molecule by itself, how would it react with other things? The only thing that it's going to be able to do is van der Waals forces, which in a large amount of van der Waals forces, that's a big deal, but not by itself. So we have to add something to these. Yeah, the carbon is really great at giving us a lot of different structures, but we have to add something to it to allow for reactions to occur. That's why we have functional groups. So functional groups are appendages on carbon skeletons. So they are small clusters of atoms that are attached. And if you look, this one is a hydroxyl group, has an oxygen in it. This one is a methyl group with a carbon and 3 hydrogens. This one is a carbon with an oxygen and a hydrogen. This one is an amino group. This one is a phosphate. Of all of these, the methyl group is the only one that's nonpolar, because all of these have very strong electronegative groups in them, and sometimes more than one. When they're bound to a carbon skeleton like these, just contain carbon and hydrogen, their presence gives the molecule the chemical properties it has. Kind of like adding a splash of color to an outfit. Hydroxyl groups are really polar because of the oxygen. These are found in sugars and alcohols. If you think ethanol is the alcohol that we find in alcoholic beverages, very polar. Methyl groups are very non-polar. They're what we find in fats and oils that tend to be very hydrophobic, because remember, hydrophobic is non-polar. Hydrophilic is polar. Charged is polar. or semi-charged is hydrophilic. So polar and charged are hydrophilic, non-polar are hydrophobic. Methyl groups have their own unique and major functions because they are involved in genetic silencing. If you think every one of your cells contains your whole entire genome, but somehow your cells all have their unique functions, and it's based on the different genes being expressed within those cells that gives each cell its unique function. What that also means is that if every cell has your whole genome, some of those genes have to not be expressed within a given cell. That's where methyl plays a massive part. Carbonyl groups are fatty acids, triglycerides, and phospholipids, carbonyl groups. Carboxyl groups are charged because they can ionize to release hydrogen ions. What is a definition of something? When we say that something releases hydrogen ions, what is that substance going to be? We talked about this last week. Is it going to be, what would it be if it can ionize to release hydrogen ions or give them up? What is a major term that we talked about last week that is involved in giving up hydrogen ions?
A substance or
Say it one more time, Jade.
substance or compound?
Well, close. So we talked about two different things that can give up hydrogen ions and other things that can take them up, absorb hydrogen ions. What were they called? What did we talk about? So when something gives up hydrogen ions in a solution, what is it called? Or it easily releases them?
Is it a strong, like an acid?
It is an acid. It is an acid. So carboxyl groups easily ionize. Another word for ionize is dissociate. And when they dissociate, they give up their hydrogen ions. So a carboxyl is also called a carboxylic acid. Because it is an acid in that it can give up its hydrogen ion. The word ionize, remember, what does it mean to be an ion?
An atom or a molecule?
An atom or a molecule that has what? What makes it unique from other atoms?
doesn't it have something to do with like the electric
It,
charge?
it does. So ions are things that have a charge on them, have an electrical charge on them. So ionizing means to break up and to become ions. So ionization means dissociation in water. It's another way to think of it. So acids give up hydrogen ions. Bases take them up or accept them. Accept hydrogen ions. With that in mind, so carboxyl groups can release hydrogen ions into solution. That's why they're considered acidic. Amino groups are charged because they can accept hydrogen ions to form ammonium ions, meaning they're considered to be basic. Phosphate groups are charged and ionized to release hydrogen ions, which means that they're also considered to be acidic. And sulfhydryl groups, if you remember, oxygen is on that top right of the periodic table. Sulfur is right below it. So a lot of times a sulfhydryl group will work like an hydroxyl group will. I want to do something really quick. Bear with me just for a moment. So I want to see something really quick because I had a class last night and we told, at least in the very beginning, we talked about similar things. And I'm pulling out some pH paper because if you look at alcohols with their OH seem like they should be able to give up hydrogen groups too. And so they should be considered acidic too. I'm curious, but they're not defined as being acids. So I'm going to move my computer back just a little bit. I don't want to spill this on my keyboard. But I have some isopropyl alcohol here, some rubbing alcohol. And I'm going to see what the pH is because I'm just curious. Give it a second. So I have my pH color scheme right here. And this is what color it turned. So it's somewhere. It's very close to staying a 7. So it's not acidic, it's neutral. So even though I would like to think it's an acid, I was just curious. Got to be curious about things. Life is an adventure. Sorry, I had to see. Any questions about these? No, generally know their structure, know their properties. Over a lot of time, we're going to learn what they're found in. So this, I'm not so worried about. This, you want to get a good idea of what their names are, what their structures are, and what their properties are. Anything that has an electronegative group in it is going to be polar or charged. Ready to come back, teaching assistant? My little dog comes and joins me, and she gets excited every time we do this because she just sits on my lap and falls asleep. She says, I'm the teaching assistant. Keep life entertaining, huh? Yeah. So functional groups can change the properties of the molecules. We have 2 different hormones here. Estradiol results in females. Testosterone results in males. Males do create some levels of estradiol, but females don't create any testosterone. If you look here, their basic structure is the same. They're both cholesterol derivatives. However, the difference in the functional groups causes their very distinct chemical properties. One resulting in a person becoming male, and one person, and the other one tends to be a female enhancing. I say female enhancing because if in the presence of normally everyone, if they never express testosterone, becomes female by default. If they have a Y chromosome and they start to produce and synthesize testosterone, they become males. If that doesn't occur, you're a female by default. Kind of sad to know that we're the defaults, but that's the way it is. So can you find the functional groups within these molecules? With time, the more time that you spend with looking at each of those functional groups, and remember, R is anything, R here is anything else. I like to think of R as being a random group, anything else. So the more time you spend with it, the easier it gets to see them. Acetylsalicylic acid is Tylenol. There's your carboxyl group. There's your carbonyl group. There's your methyl group. Lactic acid, there's your carboxyl group. There's your hydroxyl group. There's a methyl group. Aspartame, what we find in a lot of diet drinks. There's the carbonyl group. There's a methyl group. There's a carbonyl group. There's it's not an amino group, but this little bond right here is a peptide bond, which we'll talk about as a signature of proteins. A carboxyl group, an amino group. On deoxyribonucleic acid or DNA, phosphate group, phosphate group, phosphate group, carbonyl group, an amino group, an amino group, another carbonyl group, a methyl group, another carbonyl group, another amino group that we missed, another carbonyl group, another phosphate, another phosphate. So with time, you will get better at recognizing them and seeing them. The most important biomolecules in the body are the four types. There's 4 types: proteins, lipids, nucleic acids, and carbohydrates. Can also call carbohydrates simple sugars or sugars. Actually, let's not call them simple sugars. Let's call them sugars. So the 4 major organic compounds, so same thing, 4 major organic compounds also means biomolecules that comprise our bodies are what?
B.
I think you're right. B is right. So carbohydrates comes from the term hydrated carbon. These are groups that contain sugars and starches. They also contain a ratio of approximately 1 to 2 to 1 of carbon, hydrogen, and oxygen. For example, if you look down here at glucose, if you reduce that, if you what's the word for it in math when you simplify, took out a 6 of each of these, carbon, hydrogen, and oxygen, you'd be at a 1 to 2 to 1 ratio. In maltose, that S is a typo, but in maltose, there's 12 carbon, 22 hydrogen, and 11 oxygen. What makes this different? Why is that not a 1 to 2 to 1 ratio? What's missing?
An oxygen.
An oxygen, and what else?
2 hydrogen.
There's 2 hydrogen. What is a chemical compound that has 1 oxygen and 2 hydrogen? Someone besides Becky.
Water?
Water. You're right. So if you remember, we talked about when we were talking about the exciting properties of water. One of them was that it's involved in dehydration reactions. A dehydration reaction is the removal of water to connect 2 monomers together. So this is one subunit, this is another subunit. We remove the water, and that's how we get the chemical structure of maltose. Glycogen is the energy storage of animals. So we find it in the liver and the muscle. More in the liver than in the muscle. So carbohydrates typically provide a fuel source that involves redox reactions and may have some structural purposes and are also used in cell signaling. The basis of your blood types is a matter of carbohydrates. So signaling that one given cell is a particular cell and not another cell.
I know, I see you.
Cell identification. So monosaccharides, another term to introduce. Here, another term to introduce. Actually, let's introduce a few terms here. So remember, mono means one. Poly means more than one. Di means two. And tri means three, and so forth. Saccharide is any sugar or carbohydrate. Let's say in any carbohydrate. Also, many of our carbohydrates end in OSE. And so almost any time that you see an OSE on the end of a word, that has to be a carbohydrate. Saccharide, anytime you see that, it's a carbohydrate. I can't think of an exception to the OSE rule, and I can't think of an exception for the saccharide rule.
Wait, so you said if it ends in a saccharide, it's a sugar?
A carbohydrate, yep. A sugar / carbohydrate.
Okay.
Anytime that you see OSE, it's a sugar / carbohydrate. So monosaccharides, or simple sugars, are the building blocks of carbohydrates. They can be composed of 3 to 7 carbons. These pentose carbohydrates are the pentoses, pentose because there's 5 carbons, are the basis of the carbohydrate backbone, carbohydrate phosphate background of DNA and RNA. So one carbon here, 1 carbon here, 1 carbon here, 1 carbon here, and 1 carbon here. Anytime that you don't see a C here, anytime you see a bend like this, there's a carbon there. So pentose and hexose are the most important ones. Hexose meaning 6 carbon sugars. Some carbohydrates are isomers. Here's glucose, here's fructose. They have the same molecular formula. However, they react very differently. Fructose is the universal sugar and the most simply acceptable energy source for the body. Even though fructose has the same chemical molecular formula, it doesn't respond the same way. If you're familiar with high fructose corn syrup, it's pretty toxic to your body in a lot of ways. So high fructose corn syrup, meaning it's just got a lot of fructose in it. The issue with it, and especially for diabetics and pre-diabetics, is it does not stimulate an insulin response. So your blood sugars may go up, but your body is not going to be able to take fructose up.
Can you repeat that again? Sorry.
And I know it's more complex than this, but high fructose corn syrup is toxic to your body because first it has to be converted to glucose to be usable. And that takes time. Glucose goes into your body and immediately stimulates an insulin response. So you start secreting insulin. Fructose goes into your body, and even though it raises your blood sugars up, you can't remove it from the blood without an insulin response. And so fructose ultimately, over a period of time, will be converted into glucose, but not for a little while. That's why it's hard for your body, is because your blood sugars are going up, but you can't use it anyway. It's not a sugar that you can use until you rearrange it and make it into glucose. And so I think the major one that I remember, I at this point, I always look for it in juices, because if a juice contains it, I'm probably not going to drink it. I'll drink it maybe because I'm not pre-diabetic and I'm probably not anywhere near there yet. But the major one that you see it in there is, for example, Arizona teas, Arizona juices. They all, if you look at them, their first ingredient is water. Their second ingredient is high fructose corn syrup. If you are dealing with somebody who's hypoglycemic, meaning their blood glucose levels have dropped, giving them high fructose corn syrup or a drink that's high in high fructose corn syrup is not going to help them, because your blood glucose levels are great as long as you can take it up into your cells. You want your blood glucose levels to have sugars in them, but you want them to have a sugar in it that your body can actually utilize. And your body can't use fructose unless it changes unless it breaks its bonds and reconfigures it into glucose, which ultimately it will, but it can't initially. It's not a fast response. Does that make sense? Maybe.
So is that why like people drink like orange juice or apple juice, because it's more of a natural sugar? I mean, I know there's
Right.
other stuff in there, but more natural, and body can absorb it quicker.
And usually they drink 100% juices. I think, and I don't know, I haven't looked at it in a long time, but if you look at, oh, what's a good example? A Snapple, it's usually high fructose corn syrup.
Right. And it'll say like contains 10% juice or something.
Right. I mean, some of them, some of them contain lots of different juices and some sugar. But when it's high fructose corn syrup versus some other sugar, you can't use it until your body metabolizes it down. And
that takes time.
Yes. So that's just a very good example of carbohydrates that can be isomers. where their structure changes how they can chemically react and how your body responds to them.
So high fructose corn syrup is an isomer. Is that what you're saying?
It is high fructose corn syrup is fructose right here,
Okay.
and it is an isomer of glucose. Yeah, that was the basis of what I took the long way around and
Okay.
explaining it, but that's what it is. So I kind of already said this, but how might being isomers impact physical and chemical characteristics? Remember how we talked a lot initially, and I think in this chapter initially, we talked a lot about how, or actually it was also in chapter 1, how structure is very important to function. And function is very important to structure. You change the structure of something, you change its function. It's the same thing with isomers. You change their structure, you change their function. They may have the same molecular formula, but the atoms are arranged into a different structure. So some disaccharides. Molecular formulas that contain 2 hydrogens and 1 oxygen less than those observed because there was a dehydration reaction in order to produce them. Maltose, sucrose, your common table sugar, lactose, your milk sugar, polymers or polysaccharides are polymers that are chains of monosaccharides. Starch is the storage molecule formed in plants. When digested, individual glucose molecules are absorbed. It also provides a lot of fiber. So starch is a polymer of glucose. Glycogen is a polymer of glucose. Another word that we should introduce to our list of terms or root words.
Come on, I got all the animals today.
I can see your cat there, Becky.
They're my classmates, and normally they lay at my feet, but today they just must have a little bit of energy.
I can tell. Keeping you busy.
Yeah.
So glycoprotein, glyco is another way that we say carbohydrate. Anything that begins in glyco is a carbohydrate. So glycogen is a storage molecule for glucose. It's in the skeletal muscle and in the liver. When the blood sugar levels drop, glycogen is broken down and the glucose molecules are released into the blood. So we've kind of talked about this for a little while along the way, but dehydration reactions remove water from 2 monomers, like monosaccharides, and they're joined to make a larger molecule by removing the water. Hydrolysis reactions add water. If you think lysis is to break things up, hydro is water. And one more word.
Come on.
So hydro means water. Lysis or lysis means to break up or to break. So hydrolysis means to introduce a water to break up. So hydrolysis reactions add a water to break down a larger molecule like a polysaccharide into smaller molecules like mono or disaccharides. Which of these reactions are anabolic? Which of these two reactions are anabolic and which one is catabolic?
The dehydration synthesis is catabolic.
You're right, patience. Yes. And so what's the other one, the anabolic reaction? That's the hydrolysis one, right? To break it down. Which reactions tend to release energy? Which one tends to release energy and which one tends to store it?
Dehydration release.
It doesn't. It doesn't. It's the reverse. And the reason
Okay.
the reason is because dehydrations are going to make bonds, and chemical bonds are energy storage.
Okay.
So if you break the bond, like in the hydrolysis, that's going to release energy. But yeah, you would think that would be the case, but that's not the case.
Okay.
The major function of carbohydrates in the body is what?
B.
You said B is in Bravo?
Yeah, for fuel.
Yep, you're right. Which type of reaction occurs when biological molecules are broken down? Somebody else.
B.
It's B. No, wait, it's not B. So say it again.
I think it's A.
It's A, you're right. B is a synthesis. C is a synthesis. And an endergonic reaction is one that's going to absorb energy in the form of a chemical bond. So it has to be A. And remember, lysis always means to break. So lipid molecules, non-polar compounds, like carbohydrates, lipids contain carbon, hydrogen, and oxygen, but the ratio of oxygen is a lot less. 4 basic types. We have triglycerides, phospholipids, steroids, and eicosanoids. I don't know if I'm saying that right, but I'm trying.
Yeah.
Triglycerides are commonly known as fats when solids or oils, when solid, and oils when liquid. Triglycerides meaning that we have one glycerol molecule and we have three fats, three fatty acids. We remove a water to connect each of the fatty acids to the glycerol molecule. And we add a water to remove them. So this is the most efficient compact form of stored energy. When oxidized, these remove, and think oxidation, it's kind of the same as what we talked about before, but it means to introduce oxygen in this case. It probably isn't the same way where you add electrons, but or lose electrons, but I'm not quite sure. Would have to think through it. Triglycerides are the most efficient and compact form of stored energy. Deposits are found under the skin, aka being subcutaneous, where they insulate deeper body tissues. They can vary in their chain lengths and level of saturation. They can be saturated or unsaturated. When we think saturated, what we say is everywhere that a hydrogen can be attached along the carbon-hydrogen tail here. Everywhere that a hydrogen can be attached, there is a hydrogen there. So for each of these carbons, there has to be two carbon bonds, one carbon right here, one carbon right here. If it is that, and then there's one hydrogen here and one hydrogen here. If that is the way it is across the whole tail, fatty acid tail here, then that's a saturated fatty acid. However, if there is a double bond where one in between two of the carbons, there's not just a single bond, there's a double bond, which means that the carbon on this side and the carbon on this side, both of them are only bound to one hydrogen rather than two, like in the case of a single bond. That means that it's unsaturated, and it can be either mono unsaturated or polyunsaturated. Poly meaning that there's more than one double bond. Let me do this a little differently. Gonna come. Share screen. Whiteboard. Clear the screen. So I have one carbon here, one carbon here, one carbon here, and so forth, and so forth, and so forth. One hydrogen here, one hydrogen here, one hydrogen here, One hydrogen here. One hydrogen kind of here. No, it's kind of like fifth grade, right? Or kindergarten writing. One hydrogen here. Okay. Now, if along the whole fatty acid tail, it looks like this, where each carbon is bound to 2 carbons and 2 hydrogens. Along the whole fatty acid chain, that means it's saturated. If instead of this structure, so this is saturated. If instead of this structure, we have this structure, it's unsaturated. So the saturation has to do with how many hydrogen are there. And is it saturated with hydrogen or is it not? So this is an unsaturated case. If I had this, if I just have one double bond along this fatty acid chain, then it's monosaturated. If I have more than one, it's polyunsaturated. Now, one other term, and we'll see it here in 1 second, is whether or not something is cis or trans. Cis meaning on the same side. Trans meaning on the opposite side. So if my 2 groups or my 2 functional groups, like 2 hydrogen, are on, or my rest of my carbons are on the same side of this double bond, let's do this also. I have a plane that runs right here. When things are in a single bond, they can rotate around one another. A single bond can rotate around one another. When it's a double bond, it can't rotate. It's locked in a plane. It's locked in a certain configuration. And the plane is the bond. It defines the plane. We have 2 sides of the plane. We have this side over here. We have this side over here. If the bound groups are in the same plane, like these two right here, they're in the same plane, they're on one side of that bond, and they're on the same side. They're both on the same side. That's a cis double bond. If instead they are trans, one will be on one side and the other one will be on the other side. And I like to think as trans as meaning you have to transfer to the opposite side. So with that in mind, trans fatty acids, there's two covalent single bonds that angle in opposite directions. So looking here, here's my plane right here. This is going, this bound molecule is on this side of the plane. This bound molecule is on the opposite side because the plane is right here. That's a trans fatty acid. These trans fatty acids tend to resist enzymatic breakdown in the human body and remain in circulation, forming longer deposits in the arteries and raise the risk of heart disease. Cis fatty acids are where we have both of the groups that are attached to the two carbons of our double bond are on the same side of the plane. So trans meaning opposite sides of the plane, cis meaning on the same side. Are cis and trans fatty acids saturated or unsaturated? What would you say?
Trans fatty acids unsaturated and cis fatty acids saturated.
You're close, Catherine. They're both unsaturated. And
Okay.
the reason is because they both double bonds make them unsaturated.
Oh, okay.
I like that you guys answer. Let's take 10 minutes here. Let's come back at like 9:53 and get up and move around for a second. You see that I ate that one before I left. You need some A1 sauce I could try. I don't think we do. If you put it in the fridge unless it was open. I don't think there's any out there. That's all. Yeah. All these I don't know. I like it better than barbecue sauce. But I do too, but I don't add stuff. this class, I'm going to go to Stevens. Go in there. I may be there for a little while because it's the first time I've done it. And I'm not sure her email didn't exactly answer all my questions, so I'll go in there and see if I can make sense of it. And then if I can't, I'll have to call her and see what she wants.
Mary, can I ask you a quick question?
Of course you can.
For chapter 1, we had like, the workbook sheet along with like the practice test and then the quiz for chapter 1.
Yeah,
For chapter 2, when I had went on, I had only seen the thing that was due, which was, chapter 2. I enjoyed being able to print out, there was like the worksheet for chapter 1 that I was
Yeah.
able to like print out and be able to like define the terms and like,
right.
you know, all the other stuff. I do not have that for chapter 2. Is there any way
You
that
should have it. It may not be posted under that. Give me 1 second here, okay?
Okay,
It might not be posted under that, but it's there. Let me see here.
okay, yeah, just because I couldn't find, when I had seen what was due, it was only the one for chapter 2, and I didn't know how to get to anything else to be able to find that worksheet.
I thought I had it, but let me make sure. Did I not? Give me 1 second here. So it's right here. It's under weeks, September 6th.
Okay, so now am I going to be wrong for that? Because I know when I had looked over
But
to the right,
You
what
don't,
had,
you don't turn it in. I'm
okay,
sorry, say
I
it one more
don't think
time,
I
Jane.
did. I don't think I did the practice. Maybe it was the quiz. It was over on the right-hand side, what had said what was due. So I know yesterday I had did, it just came up right there where it says the assignment's due.
You know
I don't
what?
want to get hurt because I didn't click into that. So I didn't do the practice. I don't want to not submit something and then it's like lower my
All of
grade.
the practices aren't due. They will close on the 4th of October.
Oh, okay, nice. Okay,
But
okay.
yeah, they're all open right now. And I'm like, what? Your last name is Phillips. Yeah.
Yes.
Okay.
Yeah, I think I did the quiz.
I think what you are asking, that was due yesterday was the smart book assignment.
Yeah, it might have been due yesterday, but I think I've also extended it out. I thought I did. I mean, I'm gonna make sure. I thought I extended it out. Maybe I didn't. I'll extend it out. It should be extended out because we're not finished with it. I'll extend it out. So yeah, if you haven't done the chapter 2 smart book assignment, I'll extend it out. Jade, was that the answer to your question?
Yes, thank you. I just wanted to make sure that if like there was an assignment, because like I said, I didn't see the practice and I wasn't able to pull up the worksheet and it had came up differently for chapter 2 off of my end from what it was from chapter 1. So I guess I did do the smart book assignment and I'll just have to go back and do the practice test and then the final quiz for it. Thank you.
Okay, you're welcome.
I have a question.
Your patience.
Yesterday I was doing the practice for chapter 2,
Uh-huh.
and I noticed that they give me 2 different answers for like the same question.
Well, you know, some of them are they can't give you more than one answer because they're asking for more than one answer. What question are you referring to? Patience, what question are you referring to? Do you remember the question?
So like for example, the first time I did it was about mark all statements that are correct about polymers.
Yep, so that can have multiple questions. That can have multiple answers.
And then the first time it was correct, it was all the answers that were provided. And then the second time I did the same question and it gave me 2 correct answers.
Can you send me a screenshot of those questions?
I didn't take any.
Well, I'm not even sure what question it is. That's my problem.
Okay.
Yeah, when that kind of thing happens, if you send me a screenshot, I can either explain it or resolve it.
Okay.
Okay. Yeah, I'm
Okay,
sorry about that.
Oh, it's all right. Thank you.
You're welcome. Okay, so looking at continuing on with lipids, phospholipids are a little different from triglycerides because we still have a glycerol molecule, but rather than having three fatty acids chains, we only have 2. And the third carbon on the glycerol molecule is attached to a phosphate group. What is the charge? Is a phosphate group, is it polar, is it non-polar, what is it? Polar, is it non-polar?
I'm gonna guess polar.
It's polar, you're right. It's very polar because phosphate and all the oxygen on it make it very electronegative. So it's very hydrophilic because polar molecules are hydrophilic. And however, the fatty acids and the glycerol is not hydrophilic. They tend to be much more hydrophobic. So the result is that we may get an amphipathic molecule where the polar head, the phosphate groups makes the head very polar and the fatty acids are very non-polar. So when we put these into water, they immediately sequester themselves so that the hydrophilic heads are the only ones exposed to the water. And we can get double layers of them where we have one layer here, we have one layer here. The hydrophilic phosphate heads are exposed to the water on both sides, and the fatty acids are sequestered inside. These are the chief component of the cell membranes, phospholipids. I think phospho and then a lipid attached to it. Steroids are also lipids. These are fat-soluble, flat molecules that are made from 4 interlocking rings. This is your basic steroid molecule or your basic cholesterol molecule. But this little part right here, this 4-ring structure, is a signature of all steroids because all steroids are made from cholesterol. Therefore, anytime that you see these 4 rings, such as in testosterone, missing some of it here, and estrone and estradiol, they're all derivatives of cholesterol, are all made from cholesterol. So cholesterol is a precursor for all steroids.
Okay.
When the public is referring to good and bad cholesterol. So the public are actually, when they refer to good and bad cholesterol, they're actually referring to droplets in the blood called lipoproteins. You think lipo, part of a lipid attached to a protein. So these are complexes of cholesterol, fat, and phospholipids and proteins. Low density lipoproteins have a high ratio of lipid to protein, so more lipid than they do protein. And they contribute to cardiovascular disease because they store cholesterol in the bloodstream. High density lipoproteins mean that they have a low ratio of lipid to protein. So there's much more protein than there is lipid. And these can help prevent cardiovascular disease. They tend to regulate the storage of low density lipoproteins, and they promote their excretion and breakdown. One example of the risks of low density lipoproteins are atherosclerotic plaques, because they are accumulations of low density lipoproteins. Eicosanoids or eicosanoids, I think that's the right word. Eicosanoids are diverse lipids derived from a 20 carbon fatty acid called arachidonic acid, which is found in all cell membranes. The most important of these are prostaglandins and their derivatives. These are involved in blood clotting, inflammation, labor, contractions, etc. Well, I decided, because I was curious, because you remember we talked a lot about positive feedback loops. And one of the most famous examples of positive feedback loops is labor, child delivery.
Yeah.
And so I thought, well, maybe oxytocin is one of these. It's not. But its secretion, so the amount, the oxytocin being secreted from the pituitary gland is regulated by these. So just if you're curious, that's the way it works. So the 3 major subclasses of lipids include phospholipids, steroids, and what?
Triglycerides.
Right. Any questions before I just keep going forward? Any questions? So proteins make up 10 to 30% of cell mass. These are the basic structural materials and can also be enzymes. I don't know of any enzymes that aren't proteins. So all enzymes are proteins, but not all proteins are enzymes. That's the way to look at it. All enzymes are proteins, but not all proteins are enzymes. So all proteins contain carbon, oxygen, hydrogen, and nitrogen. And some may include sulfur and phosphorus. The full set of proteins made by the body is called the proteome. If you think they're your full set of genes is called the genome, Genome. Your full set of proteins is called a proteome. So your individual monomers of proteins are amino acids. The polymer is a polypeptide. And each amino acid is connected to one another by a peptide bond. This is your peptide bond right here. So we use a hydrolysis reaction to break them up like we did before. We add water. We use a dehydration reaction to connect amino acids together. And when we connect them together, we make a peptide bond. There is a test that can be done to test for proteins in a sample. And what they use is what's called the Biol solution. And it tests for peptide bonds, because if there's a peptide bond there, there's a protein there. So take out water, you produce a peptide bond. Add water, and you break it up into 2 different amino acids. So the amino acid sequence, there's 20 amino acids. And this is like a 20-letter alphabet, where each one of these is 1 letter. And each letter has its own chemical properties. They can be classified into nonpolar amino acids, charged amino acids, polar amino acids, and more charged amino acids. So positive charged amino acids and negative charged amino acids. Most proteins are macromolecules with polypeptides containing 100 to 10,000 amino acids. One change in the amino acid sequence can result in a different or non-functional protein. A result would be sickle cell anemia. So 1 amino acid change. So just like all things in biology, the structure dictates the function. So the structure of each amino acid is going to dictate its function within a protein. If you change the structure, you change the function. And so the result can be either a completely different protein or a protein that's non-functional.
Ooh.
Don't memorize this whole list. I know Becky's excited. She's going to memorize it.
Oh, yeah.
Don't memorize it.
No.
But this is just an example of an enzyme's amino acid sequence. So each different amino acid sequence is like a letter, and their various combinations can give rise to an endless diversity of words. Any questions? Any comments? We have certain amino acids that our body does not synthesize. And these are essential amino acids that need to be obtained in the diet. And they are included in this list. Any non-essential amino acids are those that are made naturally within the cell. So essential amino acids have to be obtained from the diet. I'm guessing that phenylalanine is starred there because it's one that in some people with a genetic defect, they are not able to break this down. If you're familiar, if you look at a lot of our diet drinks, you'll see on there, this drink contains phenylalanine. What it is if people have what's called, I have to remember, phenylketonuria. My mom says that's the one, so that's the one. They have a genetic defect that causes them to not be able to break down phenylalanine. This is a very easy defect to test for. And it's common enough that it's tested on every newborn baby. I don't know about home births, but I know hospital births. If you've ever had a baby or watched someone give birth to a baby, they always prick their heel. That's what they're testing for.
So like what happens if they can't break it down?
It results in it accumulating. And I think what long-term things are that it results, you know what, we're going to do this because I'm not going to keep just, what'd you say, Mom? Brain damage. That's what I thought.
Okay.
And ultimately death. You know, ketonuria. Just a sec here. So rare inherited disorder that causes an amino acid phenylalanine to build up in the body. Without the enzyme, a dangerous buildup can develop when a person with PKU eats foods that contain protein or eats aspartame, an artificial sweetener that can eventually lead to serious health problems. Neurological problems that include seizures, psychiatric disorders. I think death is also a possibility. I thought it was.
Does that also have to,
Go ahead, Jade.
I don't know for sure, but is that like, for instance, like I know during my pregnancy, they had tested both me and dad for blood type.
That's a different ball game.
Ball game. Okay. All right.
It has to do your blood type. Did you see that when I said carbohydrate markers, that
Yeah.
you're looking at that?
Okay.
And what the major thing, it's what they call, shoot, I knew it up until a moment ago. It's the RH factor, and it causes newborn hemolytic disease, anemia disease. Newborn. Say it one more time, Mom. Newborn hemolytic anemia. It is different, but it's an antibody immune response. but only if you have a discrepancy in your blood types, as my mother's giving me all this information from the other room. It's a longer story than I want to get into right here.
No, yeah,
Yeah.
I just wanted to ask. I didn't know if it was like, if that was kind of also the same thing, but I understand that it's like you said, you said carbohydrate markers, right? Which
Yeah.
is, okay, okay.
Yeah, and it has to do with you developing antibodies that
Okay.
can cross the placenta and attack the baby's blood.
Okay, thank you.
You're welcome. It's a good question though. And when you talk about the immune system next semester, ask your professor about it,
Okay,
because that's a really good question to ask during that time. If she doesn't address it, I would address it with her. So complete versus incomplete proteins. Complete proteins have all of the essential amino acids. The examples of these foods are milk, eggs, chicken, beer, and tofu. Oh, hey, there's one benefit to drinking beer. Incomplete proteins lack one or more. You can combine two incomplete protein sources to obtain a complete protein.
sorry, did you say that you could do two incomplete to make a complete?
Yep.
Okay.
Because what one, so you have of the essential amino acids, what one food product lacks in those essential amino acids, another one might have, but it may lack others. Does that make sense?
Yes.
So biomolecules, proteins have levels of structure. The first primary structure of any protein is its amino acid sequence. So this is dictated by the gene or the DNA code, the genetic code. The secondary structure is hydrogen bonding between the carbonyl and amino groups that allow for the formation of alpha helices and beta sheets. So between the carbonyl and amino groups of the peptide bonds, right here, carbonyl and amino groups, the third structure, the tertiary structure is hydrogen bonds and ionic bonds and covalent interactions between the R groups. So remember, the R groups are everything highlighted here. The basic structure of any amino acid is this right here. The R group is anything else. So the primary structure is the amino acid sequence. The secondary structure is hydrogen bonds and ionic interactions between the carbonyl groups and the amino groups. The second is interactions, van der Waals, ionic, covalent interactions between the R groups. These groups right here. two or more, and so let me stop right there just for a second. With these three levels of structure, so this is a hierarchy of structure. The third one, and down to the primary to the tertiary structure, are all within one polypeptide. All involve one polypeptide or one protein amino acid strand. Quaternary structure is interactions between different polypeptides. For example, hemoglobin is 4 polypeptide interacting. So one polypeptide can form us have structural levels up to the third one. The fourth one is only 2 or more polypeptides coming together. So, like always, the structure and the chemical properties of each amino acid in the primary structure are going to dictate any future functioning of this protein, of the protein. And so it's going to dictate what secondary structures can be formed, what tertiary structures can be formed, and whether it will interact to move into quaternary structures. And the structure is what dictates the function. Is that clear? So we have two types of proteins. We have fibrous proteins that are extended strand-like proteins, like collagen. So strand-like proteins, a lot are proteins that are parts of the cytoskeleton, display secondary folding, but do not show tertiary or quaternary folding characteristics. They're very stable and insoluble in water. They provide mechanical support and tensile strength. Some examples are collagen, keratin, elastin, and our contractile muscle proteins. These don't tend to be your enzymes. Maybe with a few exceptions, but they don't tend to be your enzymes. They're structural. Globular proteins are compact, spherical functional proteins. They display some tertiary folding and some quaternary folding characteristics in addition to the other structure levels. They're chemically active and water soluble. They play critical roles in all biological processes. And some examples are antibodies, protein-based hormones, and enzymes. Any questions?
Oh, Finley, go lay down.
So proteins can sometimes contain non-amino acid moieties, something like that, called prosthetic groups. For example, hemoglobin, each hemoglobin chain, remember there's 4 in this quaternary structure, each chain contains 1 hemoiety. I'm sorry, I cannot remember how to pronounce that word. Each one contains 1 hemoiety. Protein denaturation. So this is where we disrupt the structure of a protein. Changes in pH, temperature, and salt concentrations can disrupt the structure and thus the function of proteins. I have a question for you. How many of you like fried eggs?
I do.
Okay.
Yeah.
When was the last time you had a fried egg?
I actually did yesterday over some rice.
You had some over rice? Okay.
Yeah.
You guys are with my mom in that you like fried eggs because I don't like them. But nevertheless, this is my question for you. Is how often have you been able, you go and you crack your egg, you put it in the skillet, it turns all white. How often have you been able to pick it up, put it back in the shell, and have it turn into a chick?
Never.
Well, why not?
You've cooked it,
It's still the same protein.
but it's in a different form. Like it's a cooked form.
It's a denatured form.
Ah,
So what you've done is you've disrupted the function of the proteins. You've changed their structure and therefore destroyed their function. You can do the same thing with acid as you did with heat. I've partially hard-boiled eggs by soaking them in vinegar
oh,
because vinegar is 3 or 4% acetic acid. And if you want to, at some point, if you have little kids, show them how you can take the shell off an egg by soaking them in vinegar. And you'll actually
turn it into like a bouncy ball.
It kind of does, but it's kind of a yucky bouncy ball. Be careful with it because it will pop and go everywhere. I used to be a lab technician, and I was a lab technician for a school, and I had to pull the shell off some eggs, and that's what you did is you soaked them in vinegar, and then you had to rub the calcium, whatever calcium was left, you had to rub off. And I learned really quickly to keep myself thoroughly covered when I did that, because they would rupture on me if I wasn't careful, or if there was any defect, they would just pop and go everywhere. But they're really, really cool at the same time. Like you can do some really amazing osmosis experiments, which we'll talk about in the next chapter with those eggs. I think you can even do it with eggs that you haven't taken off the shell. But so protein denaturation can be reversible, but it may be irreversible also.
so what would be an example of reversible when you do that?
One example of reversible it let me think for a minute. Can you give me a week to figure that out? Let me
No,
come back with, you're just gonna have to deal, Becky, because I have to think about that one.
I thought that too. I sat here the whole time like, so what would be reversible?
yeah.
Oh,
Yes, you can have a week.
okay, let me think about that one. It depends on how complex the folding is and what's required for the folding to occur. There's a lot, we'll talk about it here in a moment, but there's chaperone proteins that are involved in making sure that things correctly fold. And when they're not there, you're not going to be able to make things fold back. And depending on how complex the protein is, how big is it? How many interactions do you need to make in order for it to take on the correct structure? Yeah, give me a few minutes. I'll Google it and I'll try to figure out something. But globular proteins are especially sensitive to being denatured, because realize these are the ones that are getting very complex tertiary quaternary structural changes. These are your proteins that are probably not reversible. These ones are more likely to be reversible, but they're a lot harder to disrupt too.
So like for like the fibrous ones, you said they could be reversible, which makes sense because people put stuff on their face for elastins and collagens and you know what I mean?
Right.
To look quote unquote younger, to re-energize the
Whatever
cell.
they think it's gonna do.
Right.
Right.
What about Jello?
I was thinking about that, and Jello is, I'm wondering, is it, I don't know if it's an enzyme or not. It's keratin, but I think it's more carbohydrates.
Okay.
And it can go from a liquid to a solid, but I'm not sure if it's,
How to get it back from a solid to a liquid?
oh, you can melt it.
Melt it. Well, yeah, because that's what I was thinking as far as like heating it. It's where like the structure is being altered. So
You can melt Jello, you can take it from a solid back into a liquid.
okay.
But when proteins are denatured, their active sites are disrupted. So specific arrangements of atoms within that protein structure are disrupted.
So does that mean like, oh, sorry, go ahead.
Go ahead. No, go ahead.
So does that mean as far as like, let's say if you create the Jello and then you melt it, is that where it gets disrupted? So trying to put it back into like the Jello form?
Well, let's say instead of you trying to put it back into the Jello form, because you could do that. I'm guessing you could. I've never done it, but I'm guessing you could. I'll have to try it. But what if you added a bunch of salt to it? Would it go back into the solid form? I don't know. These would be some fun experiments just to try. I may have to go out and buy a box of Jello just to see what happens. Because that would disrupt the way they come back together, because it ionizes things.
Okay.
If you think like water and how water will form those biological colloids around ions. Go back and you look at our water, when we were talking about water. I wonder if Jello will do something very similar. And when you do that, you disrupt other functions it's supposed to perform. It's a really good question. Okay, I may be playing with Jello this weekend. So specific arrangements, active sites are disrupted. These are needed to fit and interact chemically with substrates that have complementary shape and charge. So you need proteins to be able to interact with other proteins, and they have specific sites on the protein where they can interact. Well, what if you disrupt those sites and those sites are no longer available? That's what protein denaturation does. So chaperones are globular proteins that help proteins achieve their functional 3D shape. Amino acid sequences determine the precise folding, but chaperones will ensure that it's quick and accurate. So a lot of proteins can spontaneously fold into their proper shape. So let's not say a lot, let's say some. However, some, depending on how long it takes for them to fold and what parts of the molecule interact with what parts of the molecule to obtain the 3D structure, may take more time than is going to work to maintain life. So it may, some proteins may take hours or to fold when we need them within minutes. Or one part of the molecule may easily be able to interact with another part of the molecule. But in the functional protein, that part of the molecule actually interacts with another part. It's a little complex, but these just ensure that the folding is quick and that the parts of the molecule that are supposed to interact are interacting. And certain other interactions are not occurring. So these chaperones prevent accidental and premature folding and the premature association with other polypeptides. They aid correct folding and associations and promote the breakdown or damage of damaged or denatured proteins. They also assist with the moving of proteins and certain metal ions across the cell membrane. So they make sure that things are properly folded. If you see here down here, HSP. HSP means heat shock proteins, because these proteins were discovered when you tried to heat proteins and irreversibly denature them. And then these proteins would be expressed within the cell to reform the proteins. So they're only expressed upon times of stress like heat shock.
Okay, I have a,
Go ahead.
when you say folding, what exactly does that mean?
Folding meaning taking a strand like this
Uh-huh.
and folding it into the correct shape.
Okay.
Kind of like when you're folding your clothes, folding it into the correct shape and avoiding certain interactions from occurring before they're supposed to. You want to, there's a step to folding, there's a step to folding clothes.
Right.
There's steps to folding the protein so that it functions correctly.
Okay.
So chaperones are produced can be and are produced in response to traumatic stimuli, such as overheating, such as they're sometimes seen when there's a loss of oxygen to an area for a long period of time.
So would a chaperone be produced then, say, if somebody were to have like a seizure or something and they lose oxygen to the brain?
Yes, sometimes, if it's recoverable. You
Okay.
see that I think they can be formed after myocardial infarctions. They can be formed when after a tourniquet has been applied and removed. So what's important about protein folding? Sickle cell anemia is a protein folding disorder because one amino acid that's supposed to be there is substituted with another amino acid, and it ends up changing the structure of the protein when it binds oxygen. When hemoglobin binds oxygen in the sickle cell state, it forms this sickle-like shape, which doesn't flow very well through the blood and can end up forming clots. Alzheimer's disease is a result of a lack of protein folding or an accumulation of misfolded proteins. Parkinson's is the same thing. ALS, Lou Gehrig's disease is the same thing. Creutzfeldt-Jakob disease, same thing. Another one, and I think in the case of Muhammad Ali, they call it like a punch drunk effect. If you've ever seen the movie Concussion with Will Smith, if you're not ready for a tearjerker, don't watch it. But it's based on the true story of the man who went up against the AFL with regards to repeated concussions causing traumatic brain injuries. And what he saw was an accumulation of misfolded proteins. And it's the movie is really good, like I have it, but I can tell you that it's almost painful to watch at times because it was so awful. For a long time, they didn't the Football League wanted to say that that was not a case. You could not, repeated concussions could not result in mental illness long term.
That's insane.
And so they threatened his life. They threatened his wife. They actually kicked him out of Philadelphia. It was either I think it was Philadelphia. It was either that or New York. They actually drove him out of the city, and he's actually a professor at UC Davis now in California. But these are all protein folding disorders. Any change in the protein's amino acid sequence can result in serious consequences for body cells. And one thing, I'll finish this out because I'm not anti-AFL. I'm not anti the football league. If you now, they have to tell football players that they are at risk for it. And there's only a limit to how many concussions you can receive as a football player within a given time period before they'll pull you out of the game. Which two functional groups do all amino acids have? Can you take a guess? Look at the name alone and take a guess.
C and
E?
F.
C and F?
No, B.
B is in Bravo?
Yes.
You're right. B is in Bravo. And what else?
F as in fox.
You're close. You're very close. B is one of them because that's carboxylic acid. What's another one? Don't think too hard about it.
E.
E? Or what about, I'm sorry, E is in echo or D is in delta?
E is an echo.
Yeah, E is an echo.
It's actually D is in delta.
Okay.
That's why I was saying, don't think too hard about this, because that's where the name amino acid comes from. Functions of proteins do not include acting as what?
Functions.
B, genes.
Yep, you're right.
That's what I was gonna say too.
So enzymes, biological catalysts, speed up chemical reactions in living organisms by either increasing the frequency of collisions, lowering what's called the activation energy, or properly orienting the colliding molecules. I'm going to give you an example here. This is my theoretical example. Activation energy is the likelihood that two molecules are going to collide at the right angle and with the right amount of force to react and form the product. Let me say that one more time. The activation energy is the probability or possibility or the potential that two reactant molecules are going to collide at the right angle, collide long enough, stay together long enough, and with enough force that they will become a product, a certain product. So I have in this jar, I have some yellow reactants, my yellow balls, and I have red balls. And I just start shaking this bottle. I'm shaking this bottle, I'm shaking it, I'm shaking it, I'm shaking it. If the yellow ball and the red ball react at the right angle and with enough force and possibly stay together long enough, they will form a purple ball. So after 2 hours of this just shaking, 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 two of them, I've had 4 react to form 2 purple balls. An enzyme is something that I introduce in. This enzyme, what it does is it binds one yellow and one red. And it puts them, they'll bind, it has an affinity for the reactant balls. And it will put them at the right angle. So there's a binding affinity, like maybe a charge, positive and a negative charge between the binding sites here for the different ball, for a red and a yellow ball. And it puts them at the right angle. And after 2 hours of shaking and shaking, instead of only getting 2 balls formed, I get 6. My enzyme is not changed. Each time it does the reaction, it doesn't change the enzyme at all. So the activation energy is this potential or probability that the molecules are going to hit at the right angle, hit with enough force, and if necessary, stay together long enough to react. Enzymes lower that, increase or lower that let's see here, not lower that probability, make that probability bigger.
So like increases the probability.
Yeah, I always I didn't know if that was the right word. I'm a little tired. Increases the probability.
So if you add an enzyme to that, it increases the probability.
Right. And so, an enzyme that essentially is going to facilitate the reaction by lowering the activation energy. And the activation energy is what's required for those 2 molecules to come together at the right angle and with the right amount of force. Any questions about this? So chemical reactions are mediated by enzymes. An example, lactose tolerance or and intolerance. The enzyme lactase, anytime that you see the word ASE on the end of a word, that's an enzyme. ASE. Stop sharing just for a moment here. Anything that ends in ASE is an enzyme. So with that in mind, the enzyme lactase is required to hydrolyze the disaccharide lactose, which is the 2 monomers, glucose and galactose, covalently bound. So enzymes end in ASE and are named after the reaction they catalyze. Many reactions are part of a cellular membrane chain brigade. So we have a lot of metabolic pathways where enzymes work along the pathway, where the product of one enzyme catalyzed reaction is a substrate for the next enzyme. Or the reactant for the next enzyme to form the next product. And that product is the substrate or the reactant for the next enzyme in a pathway. Many enzymes only function under specific optimal conditions. So this is the enzymes are things that get easily denatured. Therefore, They need to be under specific temperatures and pH in order to work and function the way they're supposed to. Your body uses this. For example, your enzymes in your stomach are really, really amazing proteases. And if you think protease, meaning they break up proteins, they're amazing proteases. However, they only work at very, very, very low pHs. So they have to be, it has to be a very, very acidic environment. And at the normal blood pH of 7.4, those proteases that are amazing in the stomach are inactive in your blood pH of 7.4. Some enzymes are immediately inactivated right after they perform their catalytic reactions, because we may not want them to stay active like your ones in your stomach. If the ones in the stomach were active at all pHs, they would disintegrate the stomach and move out and destroy all your tissues. So we like a lot of our enzymes to only be working at specific temperature and pHs. And we want some of them to be immediately inactivated after they're done. So enzymes are globular proteins that act as chemically specific biological catalysts in regulating and increasing the speed of biochemical reactions, but are not used up or changed by the reactions. So they're not changed each time they do the reaction. At the end of the reaction, they come up with the same structure and form they had going into it. They work as chemical traffic cops. If they're not there, the reaction doesn't occur. No enzyme, no reaction. There's two parts to a functional enzyme or a hollow enzyme. Many times, an apoenzyme, which is the protein portion, and then a cofactor, which may be a metal ion or organic molecule. Do you remember that heme protein from before? That can be an example of a cofactor, or it would be more of a coenzyme. So organic molecules derived from vitamins are often coenzymes. An enzyme's blank is the molecule upon which an enzyme acts.
B.
You're right, B, the substrate. So last biomolecule, we'll start on this and we'll see how far we get in the next couple minutes. So biomolecules, nucleic acids, and DNA and RNA. So these are composed of carbon, oxygen, hydrogen, nitrogen, and phosphorus. Nucleotides are the monomers and they consist of three parts: of a phosphate group, a nitrogen containing base, and a pentose sugar. So nucleotides, each nucleotide contains a phosphate group, a nitrogen containing base, and a pentose sugar. Five major bases are we have five nitrogen containing bases. We have adenine and guanine, which are both purines. They're double ringed structures. We have pyrimidines, which are cytosine, thymine, and uracil. In RNA, uracil substitutes for thymine. So in DNA, we have adenine, thymine, guanine, and cytosine. In RNA, we have adenine to uracil, cytosine to guanine. One thing that I'll mention really quickly here is this group right here. This is RNA, this is DNA. What do you know about this group, this functional group right here? What do you remember from a couple hours ago? It's very, very polar. What that also means when you compare it up against this carbon-hydrogen bond is that this is very reactive. This is not. This is very stable. DNA has a half-life of about 500 years, which means that 500 years after you're dead, 50% of your DNA will still be around, decomposing. RNA has a half-life of seconds to minutes because of this change. So DNA major functions: holds genetic material. RNA transcribes and regulates the genetic material. We'll talk about some of this later. You'll learn about it. Hopefully you'll learn about it also in lab. DNA is double-stranded. RNA is single-stranded. The nucleotides in DNA are adenine, thymine, cytosine, and guanine. In RNA, they're adenine, uracil, cytosine, and guanine. The sugar in DNA, the pentose sugar, is deoxyribose. In RNA, it's ribose. The size for polymers: DNA is a very large polymer. RNA can be variable in size, but it's usually smaller than DNA. DNA, because of its pentose sugar, is exceptionally stable. RNA is very unstable. DNA is located in the nucleus. RNA moves out of the nucleus once it's been made. DNA is self-replicating by a complementary base pairing. RNA is converted from DNA using complementary base pairing. Give me 3 more minutes here. So with regards to base pairing, cytosine base pairs with guanine, adenine base pairs with thymine. In RNA, because we have to synthesize RNA from the DNA strand, we have to have a certain amount of base pairing here. Cytosine base pairs with guanine, and instead of adenine base pairing with thymine, in RNA synthesis, adenine base pairs with uracil. and they base pair using hydrogen bonding.
Can I ask a question quick?
Quick.
I followed that. When you said that RNA, you said the DNA self-replicates. What did you say that RNA does? It converts using what?
It replicates using complementary base pairing also.
Okay.
So it gets converted from the DNA using complementary base pairing.
Thank you.
Of course. So two major nucleotide derivatives, adenosine triphosphate, cyclic adenosine monophosphate. Adenosine, you know what, you guys, I'm going to stop right here. We're going to stop right here because the rest of this isn't going to be about adenosine. And I don't want to keep going. Did you have any, Jade, I stopped you and I made you rush through that. Do you have more questions about that?
It's okay. No, I had converted, but I had like lost you right there. So I just wanted to make sure that I had that down correctly. That's all.
No, I understand. Other questions?
So am I correct into remembering that you said you postponed the chapter 2 quiz because we didn't quite finish it?
Yes, I'll postpone it. What I'll probably do, because we will finish it next Friday, I will postpone it out until probably not next Thursday, but the following week.
Okay. It's a lot of information.
It is a lot of information. I think this chapter is by far, I think personally, it's the hardest chapter to wrap your head around.
And if you think that
There's a lot of material, but the one thing is that everything that we do from here on out is going to build on this. So this is a basis of a lot of things.
And
right.
isn't there like a, I don't want to necessarily say like tutoring, but as far as like, I know just my problem is I'm really lost looking at those like, I don't know what, I guess you want to call them charts, so on.
There is tutoring.
Okay.
And one other thing that I would suggest is put together a study group. I will put up a discussion board question where you can put in your email addresses. I would think about putting a study group together.
Can we borrow your mom too? That was a joke. That was a joke.
How about we just come to your house?
Yeah.
She is pretty amazing. I'm lucky I have her. My classes go a lot smoother when she's here. Yeah, she's pretty amazing when it comes. She teaches me a lot of things that I like. I understand the physiology. She can talk about things and I'm just like, okay, how is that happening? And then we'll discuss it and discuss it and discuss it, because I understand the physiology and I understand the anatomy a lot more than she does, but I've never done the care. And we were talking about something about atrial pauses in the heart, and I was like, what? So your heart has an auto rhythm.
Mm-hmm.
And in some people, they will struggle with getting lightheaded, randomly getting lightheaded. And she had a patient at one point who said, I don't know what's wrong with me. I feel like sometimes it's just randomly I get really lightheaded. And so they were doing an ECG on her, watching the electrical activity across the heart. And my mom went into the people who were the technicians and said, watch her very carefully and see when we miss on atrial polarization or lack of firing of the atria. in the heart. And they spotted it, and she had an atrial pause where her atria just weren't firing. And what that results in is that the whole heart doesn't contract for beats. And it was, it was very interesting to me because I was like, what are you talking about? And then, once I understood, and at the same time in my physiology class that I teach at Stevenson, we were talking about that same day.
That's funny. I work on a cardiac floor. So
Yeah.
when you say all that, I can kind of relate with the heart, all that craziness.
So you know the ECG where you see the depolarization of the atria.
Mm-hmm.
So what she wasn't getting the depolarization of the atria.
It's crazy.
Yeah, and it just, it was just, it's an atrial pulse. It just doesn't do it. But all right, yeah, she is pretty amazing. She knows a lot. I will put together, I'll put it up right now on the discussion board for this class. Oh, that wasn't what I meant to do.
I was also thinking about going to YouTube and trying to look up some of these things that we've talked about and try to find like just some really good like videos.
I would do that
so that
too.
I could get more of a visual.
I would do that too.
Okay. Do you have any that you can think
Do
of
you
off
have
the
any
top of your head that you would,
suggestions?
any suggestions?
Not really.
Okay.
Let me see if I can't find some though, because I think they would be good for all my classes.
Okay.
Give me some time to figure. I mean, one thing that I think the most abstract concept that I think we talk about in chapter 2 is electronegativity. And I think that's a hard concept to understand. And it's hard to wrap your head around. What's another concept you'd like me to look at? Do you know, Catherine?
I wasn't really thinking of one in particular.
Or you just saying all of
our,
it?
Yeah, I was gonna look at our study guide and I was gonna go through like major concepts and just look up like videos.
Let me see what I can't find, because I know in future I haven't really looked for them for this chapter. But when we start talking about bone, which is, we will make it through chapter 3 a lot faster than we make it through chapter 2, because it's an easier chapter overall. But when we talk about bone, I have some video clips for that. Let me see if I can't find some video clips. I'm trying to think what are some of the major, I think acids and bases would be a good one. Electronegativity. Atomic structure. Yeah, let me see if I can't find some.
All righty.
All right, thank you.
You're welcome.
Thanks so much.
You're
Bye.
welcome.
Have a great weekend, everybody.
You too.
Thanks.
I gotta make an egg now.
Yeah, I'm gonna get the Jello. I'm gonna try the Jello.
I'm gonna try the Jello. I think that's
Yeah.
something I need to try.
You guys.
Gervine, are you there?